Hello, welcome to this Math Day video on the ambiguous case of the the law of sines. We're going to be looking at that angle side-side situation, which we talked about in the previous video, and we're going to determine the number of triangles that can be created when you have two sides and a non-included angle of a triangle given. If you'll think back to previously in the year when we were thinking about and drawing all the possibilities of S and A, including two letters at a time, and your favorite, the side-side angle, we drew a picture as a counterexample to why angle side-side or side-side angle is actually a triangle congruence criteria. And here was the counterexample we drew. And this picture will serve us here as well. Okay, we looked at a situation with a triangle with one of the points inscribed on a circle, and we talked about triangle ABC versus triangle ABD. Both of them share angle side-side congruence correspondence, but in reality, we'll see here that they are not congruent. In triangle ABC, you have side A, or angle A, I'm sorry, side AB, and side BC. That's in triangle ABC. Triangle ABD has those same sides and angles. Triangle ABC, which I can shade a little light blue here. And if I look at triangle ABD, the big triangle, it also shares angle A. It shares side AB. And we can deduce that BD is the same as BC because they're radii in a circle, which are obviously congruent by definition. So both these triangles have angle side-side correspondence, but they are not congruent. And it turns out that this example is one of the three possibilities in the ambiguous case, in which you have an angle and two sides. The angle is acute, and the side opposite that angle, which in this case we could call it, I guess, A, is smaller than the side adjacent to that angle that the two sides share. So we get two triangles, which are unique and separate from each other. We also talked about if it so turns out that you have this situation for your two triangles where their shared angle is here, their shared side is here, and their shared side is here, we actually have a right triangle situation. So picture, when I get good enough, I'll do this with Sketchpad and make a new video, moving C and D and making them the same point and angle A being out here, we get a right triangle. And then the third situation I could give you for angle side-side is where you have the angle, you have a side, and you have a third side, but it's too short to even get to the bottom, in which case you get no triangles. So we can either get two triangles, we can get one triangle, and we can get no triangles within this one situation of angle side-side when we're trying to use law of sines, because we have an angle and an opposite side, and we have a side, and we want to solve for what opposite angle would go with that side. There are three possibilities, and we are going to learn how to distinguish when we have those three possibilities and when we don't. And I just said a minute ago, it's when you have an angle and its opposite side is smaller than this. For all other cases of angle side-side, it is much more clear how many triangles are created, and it will be 1 or 0. So let's look at the situation again. Okay, so we're going to have angle A here, and side A, and side B. And we're trying to determine what angle B would be over here for indeed having a case. Well, let's go back to what we did when we did area with trigonometry. We would use this right triangle when we drop an altitude and solve for the height, because the height is going to be a big deal. If the height is what A is, then A is here and we have a right triangle. So the sine of A is equal to the opposite H over the hypotenuse B in that right triangle created by the altitude. We are, of course, referring to this triangle right here. Okay. Which means that the height, by cross-multiplying this proportion, is B sine of A. So the height of the triangle can be found by B sine A. So if we have an angle side-side situation, there are certain number of possibilities that we can have for our angle, our side, and our side. Either the angle I give you is acute, it's obtuse, or it's a right angle. Those are the only three possibilities for angles in a triangle. And then for the two sides I give you, either they're equal, or A is smaller than B, or A is bigger than B. That is the only thing that is possible. So if we're looking at this situation, I'll erase the number I already filled in so we can discover it together. If we're looking at the picture for our ambiguous case, we should quickly realize that if A is obtuse or A is acute, if A is obtuse or A is right, that this opposite side must be the greatest side of the triangle. Because if angle A is obtuse, then the other two angles, this one up here and this one over here, wherever it falls, must be acute, and therefore their opposite sides would be smaller. So if angle A is obtuse, the only way we can create a triangle is that if A is bigger than B. So for the obtuse situation, if angle A is obtuse, then A cannot be smaller. It cannot be equal. It has to be larger. It has to be the opposite side from angle A must be the largest side of the triangle. This is the same situation if angle A is a right angle. If for some reason angle A was a right angle, then the opposite side would be the hypotenuse and therefore would have to be the longest side of the triangle. So for that same reason, we have 0, 0, and 1 down here. Okay, next, if angle A is acute. Well, if angle A is acute and A and B are equal, then that means it's an isosceles triangle. And so this angle over here, where this side comes down and meets, would be the same as this one. So therefore, we'd know this angle. We'd know this angle. This triangle would then have side angle side or angle angle side or whatever you want to call it. It would be one unique triangle. Okay. Now, if A is greater than B. Okay. Well, if A is greater than B, that means it's going to be over here somewhere. Okay. Because it's going to be longer than this one. And then again, we would definitely have a triangle that we could look at. We would definitely have only one place A could fall over here. And so there would only be one triangle. Okay. It's when A is less than B that we have that fuzzy situation. Either A is less than B and it's H, because H is the other leg and it's less than this hypotenuse with this. Okay. So if A is less than B, then we would have a situation where A would be somewhere over here. Okay. And we would have a situation in which A could be over here or over here. That's one of the places. Or we would have a situation where A was less than B, but it was still too short to even reach the other side. So if A was only, say, this long right here, then we can't even create a triangle. It's not even far enough down. We can swing it back and forth. It'll never touch this bottom side. So if we have A is less than B, then either A is equal to H or A is smaller than H, or A is between the length of H and B. H is less than A is less than B. Let's look at those three possibilities one more time. So if A is equal to H, then this will be what A is, and we will have one unique right triangle because A will be the height. So if A is equal to H, we will have one triangle. If A is less than H, okay, say something like this distance, it's too short to ever touch the bottom ray of angle A, and we will have no triangles. And if A is between H and B, in other words, A is larger than H, but smaller than B, well, then we could have a situation where A is right here, or A is right here. As it swings, over here it's less than B, over here it's less than B. We get two possible triangles. And this is analogous to the situation we learned about here. So this is where A is less than B, but A is greater than H. This one is where A equals H. And then this one is where A is smaller than H, the height of the triangle, the height of the triangle, the height of the triangle right here. Those are the three possibilities of the ambiguous case. So for this situation, we get two triangles. So what I would like for you guys to do now is practice this with some triangles. This is what we're going to do tomorrow in class, and then I'll make another video with it. You're going to look at the angles and quickly classify which ones are acute, right, and obtuse, and use that information to determine if there's any places you clearly have one triangle or no triangles. And then for the cases where A is acute, you will check if A is equal or bigger than B. See if you can nail it down. And then for the cases where you are ambiguous, you're going to have to work out the height of the triangle by doing what we discussed here as B sine A to figure out if there are 0, 1, or 2 triangles. So we will practice that in class together. So this will be kind of like our first flipped lesson.